Welcome again to the session. And the next speaker is Professor Vladimir Shikhman from the Chemnitz University of Technology in Germany.
Thank you, Juan. Thank you, Lola, for organizing this nice event. We all enjoyed it. And today I would like to present something on the mathematical programs with complementarity constraints. So we already know the type of the problems, and the picture is just what you see again, once again, for sure. And we try to link it to the so-called, what we call disjunctive regularization, and solve it. We try to solve it. But of course, the most will be on theory, how the regularization and the MPCC is connected, and then we also come to some numerical results. This is joint work with my PhD student who did his defense and is now a postdoc, Sebastian Lemmel. We looked for regularization in the last time. So, what is our problem? The class of problem. I have a little bit different notation, but the same is as in the first talk. We minimize a function, a smooth function, where we have smooth defining functions. So the function is not a problem. The problem is how they are put together, and here we have the so-called complementarity constraints. Like you all know, f1 times f2 is 0. J is the index of those constraints, so J is not important. f1 times f2 is 0, and both of them are non-negative. So if f1 is x1, f2 is x2, then you have a typical set. You also have a loop. So this is non-smooth, of course, in the point 0, and as you know, motivation applications, if you write a KKT condition of a problem or something, you get complementarity constraints of a particular type, where f1 and f2 are particular, but let us study this class of problems with any f1, f2 smooth. So we need critical point theory, so we need stationary points, and we already have heard there are S stationary points, M stationary points. What we want to study is C stationary points, Clark stationary points. We shall see. It's a little bit misleading. It's connected to the Clark differential, but not in the usual, not in the usual sense. But they call it. I mean, you cannot change the name. It's called C stationary. So, what is the critical point theory? What is the idea of our topological studies? So our invariants, and maybe this is the same idea in the second talk. In the second talk, we had a property, and we looked which subdifferential is adequate to catch this property. We do something, so the idea is similar. But our invariant is just to say what happens with the lower level sets. So you study lower level sets and how they change if they pass different points. So this is our invariant. So invariant is very, very ground-based. And the idea is that if smooth analysis can catch this invariant, the non-smooth analysis should do it too. And since topology is even more basic than analysis in some sense, we expect interesting results. Okay, that is the idea. The topology is very, very basic. So that was pioneered by Bert Jonge, nonlinear programming. Then in this 97 paper on disjunctive programming. So disjunctive programming, where Jan also did the critical point theory, and we shall need this 97 paper because we deal with disjunctive regularization. I explain in which sense disjunctive and so on. So complementarity constraints we did 2009, the vanishing constraints, general semi-infinite programming. Recently we did coordinate constraint optimization problems, mathematical problems with sign constraints and so on. So what I want to say is that you take a class of optimization problems and you look at the lower level sets. And if the lower level sets change, you get critical points, and then you need to describe how they emerge, how they glue together, and so on. Maybe you have seen, always I show this picture. This is the same picture for every talk on this critical point theory because it becomes clear what I mean. So here we have unconstrained optimization. No constraints, everything's just one function. You have mounting, usual mountains. So you have two valleys and two villages in the valleys and the saddle point, right? These are three critical points. We know derivative is equal to 0. Why they are critical? Why they are stationary? Because if you put the level, or you let the level of the lower level set grow, first you see that this minimum is born. The one component is born. Then it's blue not by chance. It's like imagine it's water pouring into the landscape. So that's why I put it blue. Think on water. So the water goes into this nearest valley. The lake grows. At some point, you reach this level and another lake appear. So that's why it's minimum. So the lower level set appears, then those guys grow, and then they come together in the saddle point. These lakes, they come together. So we have one big lake, right? And then it grows. So from the homotopy point of view, the change of homotopy type is just here, one component is born, here, one component is born, and here, you can say, one-dimensional hole is closed, because we have holes. Of course, the example is easy. In many dimensions, we can have two-dimensional holes, and the holes can appear, disappear, and so it's interesting. So, in this case, you know the minimum, how to understand the difference between minimum and saddle point from algebraic point of view. Easy. Minimum, the second derivative is positive definite. So no negative eigenvalues. That's why you have 0 component born, 0 negative eigenvalues. Here you have, in the saddle point, you have one positive and one negative eigenvalue. So something happens here, two lakes, they glue together. And this glue together is just, you can describe by, if you have two lakes, right? You can describe by taking one-dimensional interval, so taking the interval, because you have one negative eigenvalue going down to one village and to another village, like a saddle point, this is what happens. Just along the boundary of the interval, you glue these two sets together. And this is topologically homotopy equivalent to this one or to this one, right? This is just describing algebraically the change of topology of the sets. You just count the number of negative eigenvalues, which they call index. So this is algebraic invariant we want to study. Okay. How it changes and so on. Here the index is 0, no negative eigenvalues of the second derivative. That's why you need to attach a 0 cell, what to say. So this is one cell, one-dimensional cell. In this algebraic topological language, they call interval cells. And 0 cell in minimum is just the new component, right? It's a 0 cell. Of course, if the dimension grows, it can happen, you need to attach a disk two-dimensional cell. You attach a two-dimensional cell, which can close the hole or produce a hole. So different effects are possible. So it can happen, you have something like this, right? And you close the hole. Like this. And it can happen that you attach somewhere here, so you construct a three-dimensional hole inside. You just along the boundary, you know what I mean? You just attach a cell here along the boundary. It's always along the boundary. So you have cell inside, a hole inside. So one cell can be closed or can appear, and all these effects you can study by this index, algebraic index. So it's linked. This is our invariance. So it's very deep. You do not need differentiability. You need nothing. It's just lower level set, topology of the lower level sets. And the task is to describe it in algebraic terms. What is the index? For non-smooth, for complementarity constraints, we know what is index. You need to adjust index, of course. And this is what I want to present briefly, because this is our invariant we want to study, so you need to see at least once for complementarity constraints. Let's see how the index is defined in non-smooth way. Then you feel what happens. So we need linear independence constraint qualification, which is to say that the active gradients are important, are linearly independent, and important are the three sets A01, A10, and A00. That's what Jan described for us already. This is the A00, right? Where you have both 0, 0. This is A10, and this is A01. So you have J's, which are bijective. So if you live here, you are bijective, you are in the king, and here you are like equality constraint, as Jan said. But they will be important at one point. Will be important. Actually, they are not important, but for us, they will be important at some point. This is of course, this is the crucial set. But also, this will be important. We shall see. So, why we can assume this? Because we have a result saying that in also kind of topological nature of the result. If you have a set of functions and you choose randomly a problem, then this property is satisfied for this random chosen problem. Meaning that, let's say, naively speaking, if you have a problem where on a feasible set, LICQ and BCC LICQ goes wrong, this is of measure 0. A rare event. Will happen, of course, but you wouldn't see it normally. So here it is in the sense of you need to define topology on the function space and all this analytical stuff, right? And you can prove it. This is also very easy. This is just the idea of this is to say that if you have some equations which define your object, you cannot have more equations than variables. It's not so in the plane. My favorite example on this result is that if you have 3 lines on a plane, they would never intersect. This is a rare event. 3 lines on the plane never, in general, never intersect. Because 3 lines and 3 equations in 2 dimensions cannot be equal, cannot be satisfied in stable way. This is a very unstable, rare situation. You disturb a little bit, and you see that you are very, very nice intersection. Yeah, so that is behind the proof. Of course, you need to generalize, put right mathematics, but this is intuition. You just count number of equations which define you the violation of LICQ, and then you see this is more than variables. So it's wouldn't have generically this. So what is the topologically relevant point in non-smooth case, in this complementarity case? So what is the substitution for saddle point, minimum, and so on? These are in unconstrained cases, we know this derivative equal to 0. Easy. Nonlinear programming, Karush-Tucker points. We know. They have a quadratic index. This is second derivative of the tangential space. We know. Number of negative eigenvalues, so we know pretty well. KTT points, and what is the index? This is a quadratic index, like in unconstant case, but you need to take not a function, but Lagrange function, and to restrict to the tangential space. Here is different. Non-smooth case is different. MPCC is different. So you have C-stationary points, which are defined as like this. Here you have A01 and A10. These were locally, the J's were locally the unconstrained, the equality constraints. So as in KPT case, you do nothing with this. It's just gradients times Lagrange multiplier. What's interesting is the B-active case, A00. So if you are sitting here, what do you need to take? So you take derivatives of both functions which are active, that's clear. The problem is now what do the multipliers do? The sign of multipliers. So we the same explained, yeah, right? S stationarity, M stationarity have different signs of multipliers. What's topologically relevant here is both Lagrange multipliers must be of the same sign. Plus plus or minus minus. So this is just what you get. We shall see examples why. So you do not take, so plus minus and minus plus not critical. Topological sets do not change. Topologically low-level sets do not change. Plus plus is not enough. And stationary not enough. You need to take plus plus and minus minus or 0. So if you have a local minimizer, apparently it's a C-stationary point, and this is the set of multipliers. This is the set of multipliers. Recall, we have this is S stationary, right? Both big greater equal than 0, greater equal than 0. So you know that all minimizers are S stationary. This is this can be derived by Fréchet cone. If you do like derivative is in the minus normal cone on the feasible set, the Fréchet normal cone would give you S stationarity. The Mordukhovich normal cone will give you this set of Lagrange multipliers. This is the normal. This is the Mordukhovich normal cone to the physical set. Minus. So this is M stationary. If you do Clark normal cone, you convexify, you get everything. That's why I said they call it C-stationary because of different points. This is not because of normal cone. If you do normal cone of Fréchet, Mordukhovich or Clark, for Clark you get just no sign constraint on multipliers. But if you do, so this is like, actually this should be called C-stationary, but okay, the history is different. They call C-stationary something else. They call this C-stationary. This is C-stationary by definition. Okay, it has nothing to do with this normal, with the normal cone. Why they did it? Because they put, okay, they tried. Why they call it C-stationary? That also it's not very important, but interesting to know. Yeah, that's interesting to know because this feasible set you can write as min of x, y equal to 0. If you write it like this, and you take Clark derivative of min function like it were a usual equality constraint. So if you do this Clark of this min function, you have convex of 1, 0 and 0, 1. So you have, and then you write down something like gradient of f is just lambda, which is Lagrange multiplier for this equality constraint as in KPT times this guy, right? Times the of min, right? So if lambda is positive, you get plus plus Lagrange multipliers. If you rewrite the convex combination, if lambda is negative, you get minus minus. So you get exactly this notion. So they take here Clark subdifferential. That's why they called it Clark subdifferential. So it has nothing to do with the Clark normal cone. If you take Clark normal cone, it's too much. That is what they call weak stationarity. This is called weak stationarity. Weak stationarity. this is called big stationary, corresponding to the large normal. But okay, we need to live with old names. I can't change the name. Maybe it would be even logical to call it differently. But okay. If you know, now you know. So we need to define the Lagrange function, usual way, function minus the linear combination of the constraints. Here you have two constraints depending on the point. You have tangential space. Because of LICQ, you have the same dimension of the tangential space as the n minus the number of the active constraints. So you see all these gradients are linearly independent, right, from LICQ. And then you can define non-degeneracy. It's also what Jan mentioned, which says that the critical point, C-stationary point, is non-degenerate. Why we need it? Because in non-smooth case, in smooth case, we also need it in the unconstrained case to provide the theory. Because if you have flat saddle points, you cannot say much. You need a kind of really saddle points where you go down. You cannot have eigenvalue 0. Because this is like x to the power 3, x to the power 4, 5. You cannot distinguish them. They are singularities in some sense. And you want normal case of saddle points where you just know really you go down in some directions. So you need to exclude this case of 0 eigenvalues. That's what you try to do here in the complementarity setting. First you say LICQ, okay, MPCC LICQ. Then you say the multipliers for the active constraint should be plus, plus, or minus, minus. So you just exclude this guy, right? You just are here or here. Just plus, plus, or minus, minus. You exclude the x's. Because this is, in some sense, 0 cases on the boundary of this. You need to exclude. You need to go into the interior of Lagrange multiplier, if you like. And then this is what we get also from the smooth case, that the second derivative on restricted Hessian of the Lagrange function must be non-singular, no 0 eigenvalues. It is what we inherit from the smooth case. So we have a kind of smooth condition, like it were, and we have a kind of non-smooth new component with this reactive multiplier. Of course, we do not need to impose a condition on multipliers for equality constraints, as you do not need in KKT case. Equality is not important. Inequalities are important. For inequalities, you say the Lagrange multipliers are positive, non-degenerate. But for equalities, you do not need. And here too, you do not need. Okay, let us cite another result, which says that old result, which says that this property is also generic. So if you have a particular problem, a random problem, you check all the C-stationary points, you look if they are non-degenerate, then for sure, almost sure, they are non-degenerate. Idea is the same. If you have some violation of one of these properties, you get some additional equation. Some eigenvalue is 0 or some Lagrange multipliers is 0. It gives you additional equations. And then if you have too many, like with in 3 dimensions, like this example, you say, okay, cannot have it. Right? Violation of each of these conditions gives you additional equations. But Lagrange multiplier, Lagrange C-stationarity gives you already a lot of equations, right? Gradient of f is equal to something, so you have already the equation which are in the for the C-stationarity system, and they are enough. If you have once more, it's too much because you have so many equations as variables. So this is the idea. I think it's intuitively, it's not a proof, but its intuition is clear. So if we look, this is maybe important, if we look at a non-degenerate minimizer in particular, so a non-degenerate minimizer, the first condition is LICQ, the reactive multipliers must be positive. Must be positive. So this is simple to see. If you have positive Lagrange multipliers for this set in normal coordinates, is just that your function looks to plus plus. So if it grows in this direction, this is a minimizer, right? That's clear. So minimizers, since you exclude 0 plus, 0 minus, if you exclude 0, yes, this is just non-degenerate case, then this is plus plus, this is minimizer, plus plus. And if it looks into this direction, it will be settlement. We shall see in a moment. So this is the case, and here, second order sufficient condition. This is what we inherit from previous theory, that we have a second order sufficient condition as usually. On the unrestricted variable, the Lagrange function, the Hessian of the Lagrange function, on the tangent space should be positive definite. This is the old condition. You do not bother, you know. This is okay. Let us look, for example, why this is not critical. So we are in 0, 0 all the time. This is the set of typical set in normal coordinates, what they say, and our function is minus x1 plus x2. So it looks like it looks into this direction. It goes into this direction. So if you want to draw the lower level sets, if you pass 0, 0. So what we experience here is that this lower level set, if you pass 0, it's just getting a little bit bigger. And then you have a kind of second part. Yes. There is no change of topology, you see. This is just bigger. This is just a lake. The lake is a little bit strange because it's just kinked, but it grows. So that's why it's not, it's not critical. You cannot call this point critical. And this is the case for those guys, right? Which live here. Which live here. So plus, minus, plus. So this is not critical. This is never critical. So that's why if you take normal cone in Clark sense, you get V stationarity. And you get points, it's too big. That's what we did in the second talk. This is the same. It's too big, so you introduce critical points which are in the sense by no means critical. You cannot call it critical. Right? So just nothing happened. So if you have plus plus, then a new component is born. So in this case, what's below is the lower level set. There is nothing, empty. And then you get 0, and then it grows. So you have just one component is born. So the index is 0. Here, this is a minimizer, plus for plus plus. And for minus minus, you have a saddle point. This is mainly something similar to what we have seen in the unconstrained case. Here, if the function grows in this direction, you have just two lower level sets, two lakes, and then they come together. And then they glue together. So by an interval of index one cell. It's like, think on the unconstrained case. You have two villages and then two lakes, and then they glue together by a bridge. And this is what you have here. So you have one cell which you need to attach. So you can define the index here. What is the dimension of the cell to be attached? So first of all, you need, of course, to count the number of negative eigenvalues of the quadratic part, like in unconstrained case. This was not in our examples because it's like in the unconstrained case. It remains, of course. It can happen. And then you need to count the number of negative pairs, just negative pairs. Not all pairs, but just negative pairs of bijective multipliers, just minus minus. Because plus plus gives you new component. And minus minus gives you this cell attachment. So that's why the index of the cell you need to attach in order to describe the change of lower level set is the bijective index, bi, and two multipliers are negative, should be negative. That is what you count. And then you define the summation of them, quadratic index and bijective index, and you get the so-called C index. And with this notion, you can prove the two theorems, also old result. But I mean, you need to see it once because then we regularize and we study these invariants. So these are the object MA, the lower level set for A. MAB is the intermediate feasible set between A and B. And okay, compactness. So deformation says if MAB does not contain any C stationary point, then MA is a strong deformation retract of MB. Simply speaking, homeomorphic, even not even homotopic, homeomorphic to each other. Strong deformation retract, meaning that MA is smaller than MB, and you can deform MA to MB by a continuous deformation, like homotopy. That's what you see. It's getting bigger. The lake's getting bigger, but there is no change of topology. This is the deformation. And if between A and B there is just one C stationary point, which index small c with some index, some quadratic part and some reactive part. Then MB is homotopy equivalent to MA with a C-dimensional cell attached along its boundary. So you have smaller set and you have bigger set, you measure the index, and then you attach along the boundary the cell with the corresponding topology. That's what you have. So you know, this is what they call Moss theory. This is algebraic description of change of topology. And as we see here, we need non-degeneracy. So we need to prove all these results, you need C index. But C index is defined if you do not have zeros. If no zero eigenvalues, no zero Lagrange multipliers, non-degenerate case. Okay, this is generic. So you exclude singular situations. Singular situation is difficult to describe because it can happen whatever. So you can have x to the power 4, which behaves like a minimum. You can have x to the power 3, which behaves as nothing. Lower level set x to the power 3 just grow. So this is normal theory, let's say. For singularities, for every singularity you need a known theory. Every singularity is a new theory in the sense. So they are really difficult. Okay. So what we do next? So this was old stuff just for you to understand what is the invariant we study. We study index, how the index is changing, because saying index, I know what is the structure of the saddle point. Is it the saddle point? Is it the minimizer? Is it a saddle point going in 2 valleys, in 4 valleys? What is this? And now let us turn our perspective to how can we solve MPCCs, and there is a so-called regularization technique. So people try to regularize in the sense to put a T to the feasible set and just to enlarge the feasible set and then solve and drive T to 0. And this is of 2013. This is an idea to do it like this. You put F1 and F2 like they were, but you change the product F1 times F2 equal to 0 to something else. And this is something else. We make a picture in a moment. Don't be afraid. Because if you see it for the first time, it's strange. What do they do? But it is strange, but we can understand. So this is just phi of functions minus t, f2 minus t, and this is a very strange function, piecewise defined. That was the proposition, not of us, but of Kantsov and Schwarz 2013. Let us look what they mean, actually. What is the idea? The idea is very easy. I put instead of f1 x1, instead of f2 x2, just to make a picture for the normal case, what happens. So you have this kind of function, So let us look at this function in a little bit in detail. What's this? So actually what's this is the following. You have phi of x1 minus t, x2 minus t, less or equal than 0, right? and both x1 greater or equal than 0, x2 greater or equal than 0, meaning everything works in the first quadrant. You are in the first quadrant. And then you say, okay, if you put this one instead of a and b here, you have here x1 minus t, x2 minus t. You look how the function is defined. Here you have x1 minus t plus x2 minus t. So it's x1 plus x2 minus 2t. So the first case, if x1 plus x2 is greater or equal than 2t, then the product of both must be negative. Then, right, then this phi must be less or equal than 0, so a times b. So the product of x1 minus x2, x1 minus x2 should be negative. So they should be of a different sign. Let us make a picture on this. So this is x1, this is x2. This is tt. If you have here t and t, it's equal, and phi and t have 0 times 0. So tt is here. This is t and t, right? And then if you have greater or equal than 2t, which is above this line, then this is negative, or this is negative. So, and this to be negative means you are in this interval, and or in this interval. So what you have is just this set. You are above this line and in these intervals. So this is what they get in this case, and the second case is more or less trivial. If you have reverse, so if you are below this line, then minus 1/2 a squared plus b squared should be also negative, less or equal than 0. But this is also always the case. This is just minus 1/2 plus some positive. So you get also this, all these points visible. So what you have is this visible set. This is what they do. This is the idea. This is the idea. So this is the visible set. And what is the problem? So they do a theory of this. They look, they view it as an NLP. They study as NLP, normal coordinate. What is the problem about this stuff? The problem is try to, I mean, if you look at this as a NLP, you have additional inequality constraint. So you need to check LICQ, standard LICQ for nonlinear programming, just to move to the theory. But if you have gradients of this function, which in our case, a simple case, x1, x2, this is simple case, you differentiate this function. You differentiate this function. You get, if you differentiate with respect to a, you get b. With respect to b, you get a, and then you get 0, 0. If you put tt inside. Okay, so the LICQ is not satisfied. It's degenerate. Everything degenerate. That's why we got, now our idea is just take the same idea, but define a different non-degenerate way. And the non-degenerate way is to put here a maximum of t minus f1 and t minus f2. It gives you, that's why it's called disjunctive, because this is greater or equal than 0. If the first is positive, greater or equal than 0, or the second one. So it's disjunctive because of or function. One should be positive or another one because of or. So it's not disjunctive in the general, it's very particular disjunctive. With or, with this max function, you have the same physical set. Now we have critical point theory for this type of problems. Done 97 by Jongen, Stein, and Eugene. So you help us 30 years ago. Yeah, but because you see this is disjunctive optimization problem. And there the whole critical point theory has been done already. We have no time to go into this, but you can do disjunctive LICQ, you can do what is topologically relevant, you can define the C index. The idea is that C stationary points now have the condition that the active multipliers are non-negative. So you do not have plus, plus, minus, minus, you have plus, plus. It's different, a little bit different, the signs. And the index is not just negative pairs, but any pairs. Because you have just positive pairs in the disjunctive optimization, you just count the pairs. Meaning that minima cannot live in this king generically. It's not a minima. Minima cannot be here. Because it's not minimum. You can't, there is no function with making it. Generically, it's not minimum. Minimum is not in the king. That is the idea of how it works. Because minima, which we want to find which were here, generically they are never here. They move some here or here, they become usual de facto KKT points. So you think maybe it's a stupid idea. You just take here the blue set and you make it a little bit thicker. So what can change? Generically, a lot. Your minimizer from being non-smooth, having non-smooth structure, go into non-smooth, into smooth parts. So it has a dramatic change. And this topological theory just feels it. It's different because your minimizer can never be here, but can be here for MPCC. So that's why it works. How it works? So this was the research question now, how the index changing. Try to change the index. So we have, so this is MPCC and disjunctive LICQ are inherited to each other. You have kind of well-behaved LICQ relation. Then C stationary points of your regularization converge to C stationary points. You can prove under MPCC LICQ. And then the main result, first main result says that if you approximate for T with non-degenerate C stationary points of the fixed index, then the B-active index remains and the quadratic index may drop, which is okay. You can read a paper on this, and this is another result saying that it's also well posed. So if you have a point which is of the index like this MPCC, and you regularize in the neighborhood, you will find unique point of your regularization. So you have convergence and well-behaved problem, and there is also a shortest regularization, which is standard, where you regularize like this. So this is, of course, like NLP, usual NLP, where you have a quadratic, just a quadratic index. And then we tested. We tracked indices also for shortest in another paper, which is maybe now not interesting. We do numerical results. This is interesting. So we tried to compare shortest, this Hansel-Schwarz, and then our disjunctive regularization. What's better? And ours is better. So you see, not surprising if I present it, but for us it was surprising because shortest was the best for till 2001. For 25 years, shortest is the best. So there are all other regularization, shortest works the best. But our works, at least if you have normalized relative error, you have computation time, you have the violation of constraints. Ours is red. So this is a performance profile. So at least for if you want a very precise solution, it works better. Disjunctive just works better. The green is the shortest, and the blue is the Hansel-Schwarz. You see, shortest works better if you do not want good precision, but at least here ours works better. And there is explanation, of course, on this. You can explain. So why the disjunctive work? The disjunctive works because that's what we discussed. Because minima from here cannot go here generically. They are somewhere here. So you have KKT and all these NLP methods you try to solve the regularization work in a standard case. That's why there is an explanation why the disjunctive is better than to solve MPCC. Just give it to the solver. Disjunctive is better because these minimizers move somewhere else to KKT points, not stay in the king. Why it's better than Kansov-Schwarz? That's also clear. Because Kansov-Schwarz is degenerate. This was just last sentence. Because the derivative of this phi is 0. And this is what in the P methods feel is degenerate. Not good. Why does better than Scholtes? Because Scholtes worked with this product, and this is additional nonlinearity. And we work with the max function, we split nonlinearity. That's why that's intuition. That's why ours can work sometimes better than Scholtes. For example, if you have x1, x2, here you have product, x1 times x2. And here we do not have a product. You have this max function, but many solvers can do this. So we have apparently now solvers can solve this disjunctive stuff with max functions. You can put just max functions inside the solver, like in the P. That's what we did. And this is literature. If you are interested, we have a preprint. This is the last one, maybe 1, 2 or 3 weeks ago on this. Thank you, and sorry for more.